Before we end the chapter, we do a quick recap. We have thus far gone through 4 reactions involving alcohol and phenol. The first one is the neutralization of alcohol and phenol. Both alcohol and phenol can behave as an acid, but your phenol is a stronger acid than your alcohol. The second reaction that you learn is your nucleophilic substitution. In the nucleophilic substitution, you can break into 2 parts. One is where you produce ester. When you produce ester, you need to note that your phenol and your alcohol will be able to react with acid chloride to produce ester. However, only your alcohol can react with carboxylic acid to produce ester. Phenol will not be able to react with carboxylic acid. In the second part of nucleophilic substitution is when alcohol is converted to halogenoalkane. In this case, your phenol is not able to take part in this reaction. We will explain about that later. The third reaction that you learn is elimination. In elimination, alcohol will eliminate to produce your alkene. Again, your phenol does not undertake elimination. The fourth reaction that you've learned is actually oxidation. You learn that primary alcohol, secondary alcohol can be oxidized, but not your tertiary alcohol. And your phenol cannot be oxidized. In the case of iodoform test, only ethanol and certain secondary methyl alcohol can give a positive iodoform test. Again, phenol does not react with iodine and sodium hydroxide. We'll now look at the final reactions of electrophilic substitution. Electrophilic substitution involves only benzene ring. So in this case, your alcohol does not undertake electrophilic sub, but only your phenol does. So in the electrophilic substitution of phenol, there's 2 reactions that we have to run through. One is nitration, the other one is halogenation of a phenol. And before we do that, it's important to take note that OH is a strong ring activator. It means that the benzene ring in phenol is highly reactive with electrophile. And from the data booklet, it was also provided that OH group is a 2,4 director. So with that, you will find that in the nitration of phenol, you just need to use dilute nitric acid. No sulfuric acid is required since OH group is a ring activator, and just room temperature will do. So if dilute nitric acid is added, you will either get you will get mononitration, and you will go to either position 2 or position 4. If you use concentrated nitric acid, you will get full nitration. In the case of halogenation, if you were to use aqueous bromine will result in full bromination, which means the Br will go into position 246. While if you were to use bromine in non-polar solvent like CCl4, you will only have mononitration, which means the bromine go to position 2 or position 4. The reason why in the presence of water, bromine acts as a more effective electrophile is primarily because water is a polar solvent, is able to induce bromine to be delta negatively charged. Hence, because of that, bromine acts as a stronger electrophile, and therefore you observe full bromination. Finally, the QA test for phenol is to add neutral aqueous solution of iron trichloride. And why neutral? Neutral because you can't use alkaline, as Fe3+ will precipitate to form iron 3 hydroxide. And you can't use an acidic medium because your phenol will not be able to dissolve well in the solution. So you have to use neutral aqueous solution of iron trichloride. In using that, you will actually obtain a violet colored complex as observed here, and that will be the identification test for phenol.